So good day. This is Professor Ken Top, and it's Friday, the 30th of October. Halloween is tomorrow, and this is a fun time of year, but it's also an exciting time in computer architecture because we're getting into the real cool stuff, I think, when you start getting away from the concepts of how logic gates and Boolean functions operate, and then you realize people took these ideas and they created physical things, physical machines to do more quickly and more easily and more efficiently the things that we would otherwise have to do by hand. You know, this was the start of this set the stage, this process of electronic development set the stage for common production of computer systems that we use every day. And we kind of take that for granted, but basically, I wanted to tell you that just because we're going into the physical stuff doesn't mean that we are going to walk away from the logic. So even though we're in module 4 and then module 5 and module 6, closer to Thanksgiving, you're going to see that we continue to return back to logical scenarios because the basis of a lot of our hardware development originates from logical needs. What you see here is a picture of an ATM. And you have a digital or an electronics engineer who is tasked with inventing the electronics that are needed to help reduce robberies right there at the ATM. And so a lot of people know that ATMs have cameras, right? There's a camera at an ATM. And what's happened in some places is that there's been a rash of ATM robberies. So people basically walk up to the ATM and then somebody else comes along and jumps them as they're getting cash. It's usually when they're focused on the screen and they're waiting on the money and they're not paying attention that somebody gets a little too close and then they get jumped. And what some are designing is this idea of a hidden camera. But I want you to understand that a hidden camera is no good if it stays on all the time. If you had a hidden camera over a little to the side, like over to the side and lower, it would probably be bad if the hidden camera was on all the time. If this was a sidewalk and people were walking by the sidewalk and no one was at the ATM and they triggered the hidden camera, depending on the clothes they were wearing, you could get these ground up views of, you know, people in skirts, and it could be invasive in terms of privacy and such. So depending on the placement of the hidden camera, you would only want it to turn on when someone approaches the ATM. So there's a motion sensor over here by the ATM. Everybody with me? Everybody's
Yeah.
Okay, so you have a motion sensor. When somebody comes up and they start working on the ATM, you have these logical gates, right? If a person enters their card and they enter a correct PIN code and the motion sensor is turned on, then you can also turn on this hidden camera to watch behind them or to watch to the side for them, unless one of those conditions is not true, otherwise the hidden camera would be off. And so I know that we've worked up to a certain level with logic in our logic gate and Boolean functions, and I want you to know that that's not going away. We're going to keep practicing that and getting sharper and sharper at it. So when your final exam comes along, you'll have a scenario like you did, scenario A. Everybody knows what I'm talking about? Diagram A, where you either devise a complex logic gate or you interpret the diagram. And I just wanted you to be aware of that interest. But moving right along, One of the most important things that developed in terms of digital components is this idea of a system clock. So you have this capability to do and to work logical decisions, computations, mathematical, and so on. But if you can't control sequence, if you can't follow things in a step-by-step order, which is sequence, if you don't have an element of time to manage the sequence, what comes first and what happens next, it all falls apart. And one of the very first things that electronic engineers realized is that there are materials in nature called a crystalline structures, and they're crystals. And these, if you subject them to certain forces or energy, like electrical energy, if you mount a certain crystal and pass an electric current through that crystal, it oscillates for a given time, like the tick and the tock of a clock, right? And so this sense that you need a way to keep time and to track sequence is a very important thing, because you can make logical decisions, but if you can't order the logical decisions, if you can't perform them in a given sequence, and you can't make logical decisions to do one thing or another, to fork, if you will, you know, you're gonna, if yes, go here, if no, go there, then you really don't have the organic capacity, you really don't have the native capability to create a computer out of physical materials. And so early on, some scientists started to realize some of the elements were there. They just needed a way to figure out how to handle the logic to go with it. Everybody with me so far?
Yes.
Okay. So when this crystal oscillates, there's a wave pattern, and there's so many waves per second. And whenever you have so many cycles of a wave per second, that's called a hertz. Hz is the unit of measure. If you have 60 hertz, that's 60 cycles or 60 complete waves. A complete wave is defined as peak to peak or crest to crest, right? When a wave passes by a point, when the first peak hits and then the second peak reaches the same point, that's a full wavelength. And that interval of time, if it's per second, you have 1 hertz. If you do it 60 hertz, there's 60 of those per second, 120 hertz, and so on. Of course, in modern day computers, smartphones, tablets, we're working with megahertz and gigahertz. So we wanted to give you some basis for understanding what some of those terms mean. We'll discuss more of that in a bit. But that's part of the stage that needed to be set. We've already seen some of this. You recall that we had a way to switch inputs, and the multiplexer, or MUX, was one of the logic gates that we reviewed in module 3. And this is actually a very underrated evolution or revolution. I mean, this was actually revolutionary, and you'll see why in just a minute. The ability to switch inputs, given if you have an input signal and then you have other input, right? So you have an input signal and then you also have other input. The ability to send ones and zeros in to switch between the other inputs, to select or switch the other inputs, is really important. But the reverse of that, the demultiplexer, the demultiplexer or demux, is actually like a tipping point. So once they figured out how to work with selection and switching of inputs, given a specific signal, so you send in an input signal or an input selector signal, and then the logic gate knows, okay, hold on, I'm using input A, I'm using input B, I'm using input C, I'm using input D. It's switching. The reverse is true, and by reverse we mean you can use an input signal to switch between outputs. So selecting from a variety of outputs is also important, not just selecting between inputs, but selecting between outputs. And we want to stress that a demux is the reverse conceptually of a mux, in that it takes a selector input, a 1 or a 0, series of combination values, and then using that, it switches or selects on this side, on the outputs. And you're probably saying, okay, so why is that a big deal? Here's another version of that same concept. We have switches. We have the NAND gates that are arranged to create a mux. Any questions so far? Okay. So yeah, this actually is a mux with an amplifier. So that A right there is the symbol for amp. So it actually strengthens the signal that's coming out. So this is the mux part, that's the amp part. Just remember A with a triangle, that's an amp, you have voltage going in. Here's the input signal, and here it is coming out. See how much bigger it is coming out? So what can you do with a mux? Well, as a digital electronic component, we're not talking about a computer yet. We're just talking about digital electronic components. You can take a radio signal that's weak, or a sound signal that's weak, right? And then using a mux and using an amplifier, you can boost it and then make it strong and loud again. Does that make sense? Okay.
Yes.
Okay. Okay. So why don't I have all this open? Okay. So one of the things that happened, it's been said that God invented time so that everything doesn't happen all at once. God invented time so that everything doesn't happen all at once. And again, this idea of being able to work with a sequence and with time is so critical, because without it, a number of important capabilities cannot happen. One of the first things that cannot happen is a CPU. Central processing unit, or an arithmetic logic unit. You'll remember from von Neumann's diagram, the arithmetic logic unit, the logic gate digital component that you can build out of NANDs or NORs. This is used for computation or data processing or mathematical calculations. And so that particular component is only one piece of a CPU. There's also memory registers. So we have something that's going to actually be the engine of data processing, but we also need to be able to store input values and output values, and we have to be able to store instructions. That's where the RAM comes in. And there's a little bit of memory in the CPU. The ALU is one component, and then sitting underneath the ALU in the von Neumann model is the register. That's those are memory chips that are closest to the ALU, and then controllers. Well, here's the part that gets crazy, and there are some links in the draft of your new study guide. So the module 4 study guide is a draft, but there's a link right here, and I want to show you this link. I want you to spend some quality time in this website. You should have seen this before. This is not supposed to be a surprise. You're going to say, oh, I remember something like this from the previous modules. But just as we talked about crystals being the basis, the physical basis for an oscillating signal, we can start using for a clock on a computer. You have these physical substances made out of metal oxide silicon. MOS. Everybody repeat after me. MOS. MOS. Or MOS.
MOS.
MOS. Or MOS.
MOS.
Yeah.
MOS.
So you say CMOS or CMOS, right? Okay. The thing that I want you to know is that it's a field effect transistor. So you have these materials that are complementary. You have metal and you have silicon and you have oxygen. And what's silicon oxide? It's sand. If you take quartz sand and then you process it in a factory, and then you start blending it with some metals in a complementary fashion, you end up with this substance that allows you to manipulate electric signals with the effect of electricity and magnetism. It's a field effect, so they're called field effect transistors, or FET. Now I know in the Virgin Islands, the word FET has a different connotation, yes? I'm sorry, I couldn't resist that. I thought that was too cool. All right, so anyway, if you take these substances of one type or another and you combine them, so there's an N type and a P type. If you have an NPN combination or a PNP, those are specific types of electronic components that mimic the behavior of logic gates, right? Now I'm oversimplifying things, but just accept my word for that for now. Just remember that MOS or MOS means metal oxide silicon, and FET means field effect transistors. CMOS or MOSFET, I want you to know what those mean. JFET, right? I want you to know what those acronyms mean. So we have some developments on the physical side. Scientists are moving things along, and the mathematicians are working with the logic and the Boolean functions. And what happens next is that somebody figures out, yes, how to do calculations. And this is some brief information here about the way that we carry numbers during certain mathematical operations. Yeah, the logic has to process this in a specific order, and it flips some things. It's called the radix complement. So you have to use a logical algorithm, a logical method that involves a mathematical concept called the radix complement, or 2's complement method. And you know you can't have anything higher than a 1 or a 0. And then you have negative numbers. So how do you do calculations with negative numbers? It's easy enough. We can do on paper, we can use and or to multiply or add two binary values. We've already done that. What we haven't done is added or multiplied binary values that are negative, right? So in order to do any kind of real math, you have to figure that out. And they did with logic gates, and it was called an adder. Except that it didn't really, the first half adder didn't carry the 1 when it calculated. So they worked a full adder and a multi-bit adder to solve that problem. So you may see a question about a half adder. It was the first example of an adder, only it couldn't carry the 1s. And so in order to work more efficiently, they came up with a design called the full adder. And they flipped it and then included more bits. So just like you can have a 4-bit AND, you can have a 16-bit ALU. Oh, you should see the HDL for that. You should see the HDL for that. It's really interesting. But as you start to get more and more as you start to become better versed with how to use HDL, you're going to find out that simple but elegant designs are really powerful. So you would think, oh my gosh, this is going to be terribly complicated. Not really. in principle, what you see here are 16 bits in and 16 bits out. So 16 bits go in parallel and 16 bits come out. And that's where we get into this idea about, wouldn't it be nice to be able to switch between inputs or switch between outputs, right? So just let that ruminate for a little bit. But that's not the magical ingenious invention. The thing that flipped this thing, the thing that got this whole scenario off the ground like a rocket, is this notion called the FlipFlop. So using logic gates, they figured out a simple circuit that sort of rolls the value and flips it, and then with the next operation creates the same value. And that seems like, so what? That's like a juggler who throws the ball in the air and then he catches the ball and then he throws it in the air again and he catches the ball again. And he throws the air and you're like, I'm bored. I've seen jugglers before. It's not a big deal. Logically speaking, you have a certain time increment that's involved with the input, and then what comes out is the same value that went in. Again, it cycles, right? So this is the logical statement that does the same thing. And you're probably saying, okay, yeah. But if you take a mux, can everybody see this?
Yeah, we can.
Yes.
Okay. So this is a working DFF or digital flip-flop, right? So what goes in comes out. And you're like, yeah, I still don't get why that's a big deal. I put something in, I get the same thing out. Yeah. I can do that with a wire, can't I? No, you can't. Because if you loop it and then you stick a mux in here, what you end up with is something amazing. You have a 1-bit memory register. Let's repeat that. You have a memory cell on the smallest, most microscopic level. You have a 1-bit memory register. This is the same memory register that's used in the registers in the CPU. Now you have a CPU that can store temporary values for the instructions and for the data. So it has a place to work those things. Before you didn't have that. Now your CPU can work. The CPU design we looked at before could only do certain things and only if you forced it manually. What am I saying? The adder, the half adder and the adder that was developed. Yeah, you can do things manually. You can click the button to make it execute. But who wants to sit around clicking buttons a million times a second to make your computer work? Let's repeat that just so it sinks in. It's nice to have a machine, but if you have to use it manually and you have to take every step by yourself by hand, what good is it really? Right? Don't you want something that'll automate it? So this little invention here was like the first gear that ever went in the first engine. All of a sudden you have a way to store instructions and the data that the instructions operate on. Now you have RAM. Once you move that data or that instruction into the CPU, you have registers to process. So if there's intermediate results, you can store intermediate results, temporary output, until the calculation can finish, right? So this was the beginning of the magic. This is really where electronics exploded like a rocket off the launch pad, because the last piece that they needed to make everything a reality was realized, right? So this is no small deal. I want you to memorize the logic, the truth table, the diagram, right? This is the interface diagram of a DFF. Here you see the interface diagram of a MUX, you know? It's used to select. So when something comes out of here, it's split. You have one value coming out, but then you have another value that's cycling back around. And the MUX goes, oh yeah, I'll take that again. So if you don't have anything to catch it on the other side, oh yeah, I'll take it again. Logically speaking, that's what's happening here. Does that make sense? Kind of, sort of, maybe?
Yeah, it does.
Yeah.
Yeah. So you have ones and zeros, a pattern of ones and zeros you can recycle. As long as you have electricity, you have a memory bank that recycles those ones and zero sequences. And you have memory registers. A register is simply a storage space that holds ones and zero combinations, right? And it's monumental. I mean, that's where, okay, now we have all the pieces we have. Now we have all the pieces we need to make an engine. So now we can have automobiles, or we can have power tools, or we can have, you know, on the digital level, this is really kind of a tipping point here. We talk about random access memory, and it is non-persistent memory. One of the most important things to understand about RAM is that it has to refresh. It has to have a constant supply of electricity. If you don't have electricity to loop the ones and zero combinations to keep refreshing those combinations, when the power goes off, you lose the ability to do that, and anything that's in RAM goes bye-bye. That is the one piece that made the CPU and RAM possible. There is one other piece. We're going to save it for module 4. No, module 5. Maybe even module 6. Okay. Do computers lose all of their data and instructions when you turn off the power? I know that's a trick question, but I need a volunteer to respond. If I turn off the power with my computer, do I lose all of my data and my instructions on that computer?
No,
No, you won't.
no, no.
No.
The short answer is no, you're correct. I don't lose any of the data or instructions that are stored in persistent memory on the hard disk. So I have data storage that's persistent in the form of a disk. And basically, once I have that disk, now I have a way to load the memory, load the registers when I turn it on. So the hard disk is the other piece. In the von Neumann diagram, it's on the I/O side, and we don't even have a box that's labeled hard drive, do we? On the von Neumann diagram, you don't see a component called hard drive, do we?
No.
Nope, that's because you can load, you can store data permanently by using cards, computer cards. You don't have to have a hard disk. As long as you have a physical way of storing ones and zeros, you can work a whole variety of things. Here's what I'm talking about. They're called punch cards. Has anyone seen anything that looks like this?
No. Mm-mm.
Okay.
No.
Well, has anyone seen a cassette tape player?
Yes.
Okay. So cassette magnetic tape and these data cards, everywhere there's a punch, that corresponds to a set of ones and zeros. So this is kind of like a USB thumb drive, old school. Only it's physical. If this mildews or it ruins or it burns, you lose your data, right? So these punch cards were stacked very high, very thick, and a card reader would feed them in one at a time, one after another, after another, after another, and all of those ones and zeros would be interpreted, all of those punch holes and their placement relative to the marks, the indexes. The computer said, okay, that's a 1011, 0111 kind of thing. That's what was happening here. for mainframe computers, before they had PCs, before we had smartphones or tablets. They had mainframe computers. And this took a long time. It took up a whole room to store a machine that did all this. It was huge. In any case, in von Neumann's diagram, you don't see hard disk on the picture because you don't need a hard disk to run a computer. You just need a way to feed in ones and zeros. And it's important to understand that persistent memory can be coded in all manner of physical resources. DNA, right? There's anything where there's a repeating pattern that can be manipulated, you can encode ones and zeros in that pattern. So it doesn't have to be, but to make a long story short, scientists did figure out that if you take a disc like a record player, everybody knows what a CD or a DVD or a record is, right? Spins around on a platter, spins around and around and around. You can encode those ones and zeros on that, and that's what the disks are, the hard disks are. So, okay. So in our investigation of components, we are going to take this revolution. Now that we have memory and we have the computing component, we have an adder, it's working. We have a digital flip-flop, so we have the adder. Where's my adder? Well, there's my adder, my ALU. So we have the components we need for the ALU. We have our digital flip-flop. We have memory registers now. Now we can build other components, and I want you to get a flavor for how rich this is. These are two of the images and two of the digital components that allowed a personal computer to be invented. This is called a digital signal processor, or DSP. How many of you have listened to a recording artist use auto-tune and it automatically changes their pitch so that they always sing in tune? Does anybody know what I'm talking about?
Yes.
Okay. So auto-tune would not be possible on a hardware level without a digital signal processor, which is shown here. In physical terms, you see the logic gates are ANDs, but that's overlaid on the metal oxide silicon field effect transformer MOSFET circuit material, right? So embedded in there are these material versions of the AND logic gates. And what you have is a very simple digital signal processor. That allows you to communicate. So communicating with and between computers also requires another digital component called a UART. So you have to interpret the signals that are sent, and you have to encode the signals that are sent. That's where the digital signal processing occurs. But then you also have to receive and transmit. Let's repeat that again. In order to communicate between digital systems, to do networking or wireless or cellular stuff for your smartphone, anything that sends and receives digital information, you need to be able to digitally process the signals to render the ones and zeros or encode the ones and zeros. That's where the digital signal processor, digital component comes into play. But once you have that value, or you have that information, you have to be able to receive it and transmit it, which is why we have another digital component called a universal asynchronous receiver transmitter. Universal asynchronous receiver transmitter, or UART. These two components together allow you to send and receive things like wireless data traffic or voice transmissions on a smartphone, right? Or faxes. So what am I talking about? Does anybody know what a fax machine is? What it does?
Yeah, I know what it is, but I don't know what what it does. Like,
Okay, well, that's a fair answer. we had phone lines for the longest time. And if you had an old-fashioned telephone line and you called New York City from the Virgin Islands, when the phone line rang through to connect, a copper wire, a physical copper wire was connected from where we are in St. Thomas or St. Croix, all the way across the ocean, all the way through the switching centers, all the way up to New York and back. And a continuous copper wire circuit was formed. Let's say that again. That's no small feat. The first telephones connected you physically with copper wire, no matter where the call was, who the caller was and who the called person was. On the other side of the world, that wire had to carry an electric signal. And you basically talked, you converted the sound into an electrical signal that carried across the wire, and then when it got to the other side, the speaker reproduced, it turned the signal back into sound again. That's what Alexander Graham Bell invented a long time ago. So 100 years later, everybody has a phone in their house, but we don't have computers yet. And then we start getting computers when they start realizing, oh my gosh, we can build PCs. Everybody can have a computer in their home. And how do you connect them? How do you do more than just one computer at a time in one location? Well, you connect them all, you make a network. How do you do this? One of the first ways we did this was using modems. And we also needed to communicate large volumes of paper. So instead of using the US mail, sticking it in an envelope, having a carrier put it in a truck, putting it on a ship, carrying it over to another carrier who was on another truck to bring it in your mailbox, we started taking paper and creating a facsimile or a likeness. The word facsimile means likeness, a likeness of the physical paper in digital form. And then we used the phone line with a fax machine. The fax machine was built from something called a modem. There's a, well, and a DSP. All right, so it's a little more complicated than that, but basically we used the phone line to embed digital information on those same electric signals that people's voices were carried on. And it was a squeal. It was a really strange squeal. It would modulate, and then on the other end, it would demodulate the signal, the squeal, back into ones and zeros. I'm going to see if I can find a quick representation of this in YouTube, just so so you can hear it for a second. So this electronic, can everybody hear that?
Yes.
Yep.
It's kind of annoying, isn't it?
Yes, it is.
Yes, but each of those chirps are actually made of thousands of mini chirps and bursts and pauses. And those are, so the sound signal is processed into electrical signals with bursts and peaks and valleys and waves and all that. And then on the other end of the phone line, it's all put back together again. It's modulated into sound and then demodulated from sound back into digital ones and zeros. And that's the first kind of networking that we were able to use with our telecommunications systems back in the day when it was just telephones. This was also, modems were also used for connecting to the internet, the first internet. So if I say modem now, sound of a dial-up internet, right? So here's another sound of the dial-up internet.
Oh, yeah.
Did everybody hear that? Same kind of thing, right? You're taking audio and
Select memory.
yeah, yeah, it's actually, this was very slow. You had to use a telephone system and you had to connect the modem on your computer into the phone system. And if there were lightning storms, this was the fun part. If there were lightning storms that rolled through the areas, a lot of times phone lines would pick up the lightning surge and it would fry your modem. It could even fry your computer, right? We don't worry about that now with wireless, do we? I mean, not really. We don't, we've come a long way. So I'm kind of sharing a bit of dinosaur stuff with you right now. But before we close, I want to share just a few more things with you, okay? In order to make a computer happen, we're going to spend module 4 examining all of the different and amazing digital components that are used to build a system. We're not going to discuss how they're assembled into a system on a motherboard until module 5. And then we'll talk about data center and cloud stuff, the real computing platforms on steroids in module 6. So we have some really cool stuff ahead, and I'm excited that this class is going to be able to take computer architecture further than any of the classes before you since I've been teaching at UVI. So again, I'm proud of the performance that you logged on your midterm. But I wanted to show you a virtual machine. So here's the hardware components. Can everybody see my screen here?
Yeah, we can.
Yeah, I see.
Okay. So I'm going to show you what's so amazing about this in just a minute. And I'm hoping that somebody, if they think about it, will actually gasp or say, wow, I know that's, I'm kind of forcing it here, but this is the computer management module for my Windows operating system. And it reflects the physical, the actual hardware that my laptop is using right now. And these are all of the digital components from the processor to the network cards, to the disk drives, to the display adapters, to the actual monitors themselves so that I can see things on the screen, to the keyboards and mice. All of those devices have to be used, right? You think about what goes into a computer, the sound, the video processing, the security devices. I have printers, right? You have print queues. Storage controllers, those are the circuit boards that control the hard disks. We have USB connections, so we can plug in USBs and printers and all sorts of cool stuff, webcams. Yeah. Inside here, inside the system on the motherboard, we have memory controllers, we have PC Express. So we have digital expansion slots. We plug in memory modules. We have memory controllers, memory access controllers, right? All sorts of cool components. But from where I sit, that's not the most mind-blowing piece. You see, memory, that digital, that lowly digital flip-flop, and that mux. When we start our physical laptop and start running it, I can create a whole virtual computer with virtual hardware components built from virtual logic gates and digital components, including the memory, the processor, the graphics, the displays, the storage, the audio, the network, and all of this virtual digital, all these virtual digital components are assembled and working together, and I am running a full-scale Linux system, a computer system, in memory, in RAM, while I'm running a physical system with electricity. So I have real hardware digital components running with real electricity and electromagnetic signals, but because of the way that memory has progressed, in terms of its capacity and its complexity and the way CPUs work, I can build a virtual system that runs. I can have a system, a computer system running inside my computer system. And it's all in memory. Every one of these virtual devices, the shared directories and folders, USB drives, serial connections, network cards, wireless and Ethernet, audio, right? I can do gaming on this thing. And it's a virtual machine running in memory inside the real physical hardware on my laptop. So we've progressed to the point where we can have computer architecture running within inside other computer architecture. I don't know if I'm failing in terms of how I'm articulating that, but to me that's kind of mind-blowing when you think about what's happened in just the last 25 years. Much of the things that you use now uses this technology, but absolutely none of it, not the first piece, would work at all if you didn't have this. The memory register. Okay, and then you also need a way to store ones and zeros. Are there any questions before we close?
No question.
No.
I'm going to have some short assignments for you. I'll put the first one out over the weekend. You'll do some independent reading. You'll watch some YouTubes, and then you'll engage some things. There is a draft of the study guide, what you're seeing right here, right now. It is inside, oh shoot. It is in Blackboard. So basically, where is my Blackboard? If you go to Module 4, you should see Module 4. You should see the start of the student learning objectives. And I've lined up some of the stuff that we're going to be doing. But I'd like you to get started reading. Much of what we're going to read going forward is not in your textbook. There will be a few quick things we reference in our textbook going forward, but much of what we're going to read moving ahead from this point is going to be online. So you're going to need more access to the internet, and you'll definitely need access to the linked references in the study guide. And this is the first link in the study guide. So as you go into these other, there we are. Oh, that's what I was looking for. Can everybody see Module 4?
Yes.
Okay. So I'm about to replace this. I'm going to take this down and push another one out there, but I want everybody to read as much as you can and click the links and start watching the YouTubes. And we'll see you Monday. I hope everyone has a great weekend. Are there any questions before?
Quick question, Professor Kenta. Are we meeting on Monday since it's a holiday?
Is it a holiday?
Yes.
Liberty.
Yeah.
Is you notice for UVI though?
Is it, if it's not a UVI holiday, then we would meet.
Oh,
Okay. Because
why
I
don't-
know my calculus class, he was like, it's a holiday at UVI, so there was no classes. So.
Why don't we
Okay.
find out? Why don't we find out? You
Okay.
said calculus told you this?
Yeah, my calculus teacher.
I'm pretty sure your calculus teacher is, you know, I didn't even think about that.
Professor Rapp. That's my.
Yes. So fall semester 2020, Liberty Day. We do not have class on Monday. We have class on Tuesday. I'll see you on Tuesday. I'm so glad you asked that question. Thank you.
Yeah, you're welcome.
Okay. Well, I'm going to go ahead and stop sharing. Any other questions before we